Hi, my name's Russ. This is a video in the series of videos being created that review some of the fundamentals of fire forensics as defined in NFPA 921. This discussion will be on the calcination process of gypsum wallboard and how it can be used a tool at helping to define fire patterns in a structural fire. So calcination involves the reduction of gypsum by basically dehydration. So it's a chemical and physical change. Gypsum is, its official term is calcium sulfate dihydrate. For every calcium atom, there's two water atoms, or water molecules. And when you heat up gypsum to 100 degrees Celsius, it results in 1.5 of those molecules, moles, loss of your water. And there's both a dihydrate and anhydrate version combined in gypsum. You lose the other 0.5 mole in this process as well. So the water is evaporated, and what that leaves is a reduced density of this calcium. This gypsum has a lower specific gravity, and that difference you can calculate because it's a function of energy exposure over time. And you can use that because the energy exposure is going to happen more rapidly when this material is closer to a fire of a given size. So that's how the principle works for this process. One thing that is frequently misunderstood is that coloration is an indicator of calcination. That's simply not the case. You don't have to have any color variations to indicate that the calcination process has occurred. But what does happen is because of a lower density and a softer surface, you can actually measure depth and use that to basically gauge how far the calcination process has gone. What coloration can do from the lines associated with soot deposition is identify, based on what we've already learned about ventilation controlled fires and clean burn and things like that. You can tell from the patterns on the wall where it may have had more heat exposure. And that's how you can basically narrow down on where it might be beneficial to take these measurements. So depth of calcination is a function of energy transfer. Comparisons of calcination depth measurements will create a contour profile of a given wall that defines energy transfer for various points. And what those contours can do is they can point to higher sources of energy that were exposed to the gypsum. Consistency and measurement protocol must be maintained. So anytime you're doing any kind of field measurements, you always have to be consistent in the methodology, the tools that are used, the pressure that's applied. Failure to be very consistent is going to bias your data. Probably the most important feature is that suppression activities can impact calcined gypsum. Hughes Jensen did perform a study on this. They recorded an 18% reduction in depth measurements after 24 hours from when the calcined gypsum had water applied to it. So what effectively had happened is water did penetrate into that calcined gypsum, and you had it change its density, and consequently the depth measurements changed. Now, what was interesting about that study is when they waited for 30 days and allowed that gypsum to dry out, there was only a 5% reduction. So if you did have situations where measurements were critical and suppression, let's say an automatic fire suppression system was involved or manual suppression, then waiting until the gypsum dried before taking those measurements would produce more reliable results. So here's a couple examples from NFPA 921. You could use a standard caliper with the back end measurement device or a depth gauge. Either one works. This is kind of an interesting chart. This is a Hughes Jensen chart. A few minor mistakes here. Now, what this did is it analyzed half-inch gypsum and 5/8-inch gypsum. So if you consider, they took this measurement a little too far for half-inch. If you consider this, what this effectively says is after 400 kilojoules, you've basically, gone through the entire penetration of your half-inch sheetrock, completely exhausted of its water molecules. The other thing I don't like about this particular chart is it's in terms of kilojoules, and that really doesn't give much meaning. What I assume happened is it probably is more on the order of kilojoules per square meter, some kind of area density for energy. So keep that in mind if you're using this chart. Feel free to look up the Hughes-Jensen analysis for more information. But you can see that 16 millimeter 5/8 inch gypsum, it's going to last longer. And the reason it lasts longer was on that second slide, is that basically the chemical dehydration process. You're basically losing water, and that's why sheetrock is such an exceptional fire protection material. Here's an example of a room that had a laboratory test fire performed in it, and then grid patterns of 1 foot by 1 foot were drawn. And then what was done is calcination depth measurements were conducted, and a contour map was created. And this just establishes how you would do it. Create a map from your measurements, and it could target a particular location. Coloration cannot be used to indicate degree of calcination, but it can help you in determining where an analysis should take place. Calcination depth measurements can produce a contour chart that point to a higher source of energy transfer. Water can impact the depth measurements, so suppression water will bias the results. This whole process is really not overly reliable. I did give a char presentation that was, I think it's presentation number 1 in this series. Keep in mind, there's a lot, I think I mentioned in that it was a fairly reliable measurement tool, but let me add a couple caveats to that, both that and as far as calcination measurements. You have to have consistency in terms of your heat flux, in terms of the situation, the circumstances, the surface finishes. There's a lot of variables. So generally speaking, whether it's char depth measurements or calcination depth measurements, and then charting those depth measurements on a contour plot, they may have some value, and it's just one tool in a quiver of potential tools that are available to the fire investigator, but they're not foolproof. So there are some weaknesses. Also, there's some differences between Type X and regular. So let's say I go to Home Depot, I pick up some 1/2 inch sheetrock that's not considered a rated material. Your Type X, your 5/8 inch sheetrock, you use that because it can give you, basically an hour of protection. But the difference between Type X and not Type X is basically glass fibers within the mix. And what that does is it holds the sheetrock together, the gypsum together, during this calcination process, and it prolongs its life. So that's why Type X is for rated applications and regular is not. Another thing you're seeing is low density gypsum. So you're seeing a specific gravity that's, roughly 0.7, and typically sheetrock is a little heavier than that. So it's a lot heavier than that. So depends on what version you're looking at, but you have some lightweight sheetrock that actually has a density under 700 kilograms per cubic meter. And as far as performance goes, make sure when you're looking at it, for residential applications, you're looking basically for interior finish. That's what drives it. Chapter 26 of the IBC does require 1/2 inch gypsum over expanded plastic insulation. But otherwise, there's really no reason why you couldn't use lightweight sheetrock versus non-lightweight. But as far as fire performance, whether or not, I would have a tough time thinking it's rated. But just be aware of that. That's something that's starting to happen more frequently now, and clearly it's a different material. So be aware that there's some subtle differences there. In any event, thank you for your time. I hope this was beneficial. Calcination is one of several tools that NFPA 921 describes. We'll be going through more of those as part of this series. Thank you for watching this, and have a good day.